So Muaz, would you like to, I think you guys agree that there's no recording of the presentation. I believe there's unpublished data. Is that right?
No problem. We can record the presentation. So, okay.
So,
okay.
Is it okay to record it or not? I self-recorded, but if it's not,
okay. No problem for me. I mean, you're asking the other attendees.
Okay, that's great. Thank you.
Okay. Thank you.
All right. It's my great pleasure to introduce our speakers today, Dr. Muaz Kemerli. He is an assistant professor in mechanical engineering at the University of Sakarya in Turkey. Muaz completed his master and PhD at the same university, and he holds a bachelor degree from Yıldız Technical University in Istanbul. His background is computational fluid mechanics with a specialty in non-Newtonian fluids and turbo machinery. So Muaz is currently visiting our department since summer as a postdoc researcher funded by the Turkey government. And he mostly had been working with myself, working with particle-laden flows in biomedical settings. So thank you so much for accepting to give us the talk today. Without any further delay, I'll let you present.
Okay. Thank you for your introduction. So let me just first share the slides. Sorry. So you can see the screen, or
yes.
Just a second, I think.
Okay, it disappeared now.
Sorry. Okay, I think now it's working. Okay.
Yep.
All right. Okay. Thank you for your introduction, and I'm really glad to be here sharing with you some of my experiments during my PhD study. So I just arrived in Toledo 2 months ago, and we started working with Dr. Emily. As he said, I'm a visiting scholar here, and we are working on the particle-laden flow biomedical applications. And so I'm going to present a seminar about my PhD study, actually. So my PhD study was about the magnetorheological dampers, and I want to share this experience with you. So my study was actually an implementation of MR dampers on a building to damp the seismic vibrations. The viscous dampers are being used in buildings for a long time, and the magnetorheological dampers is a different type of a damping device. It's not a viscous damping device. It's actually adjustable viscosity dampers, or adjustable stiffness dampers, we can say. And what makes it possible that the fluid inside of the damper, it is called magnetorheological damper. So it's called magnetorheological fluid. So this fluid is a special fluid and can be manipulated by changing the magnetic field, and you will have a chance to manipulate the stiffness of the damper, so you can make a semi-active control for buildings or for any type of application. So I put the video as well from our experiments, just to show you how the magnetorheological damper can damp the seismic vibrations. Okay, so I'm going to begin my presentation with the AMAN scope. I just put a flow chart to just know where we are. I'm going to start with the AMAN scope, and then I'm going to focus on the MR fluid and the MR dampers. And then I'm going to speak a little bit about the characteristics of the MR fluid and the models in the literature. And then I'm going to present the CFD model that we were using. And I'm going to speak about the CFD approach in details because my PhD study was, the core of my study was the CFD approach and the CFD modeling of the magnetorheological damper. Of course, this is a larger project actually. So my study was a part of the study. So I wanted to show you the whole project as well, along with my study. So I'm going to speak briefly about the other parts of the project as well. And then we are going to cover up all the results, and I'm going to give you some concluding remarks in the end of the presentation. So our scope actually, I can say briefly what we were doing is literally implementing an MR damper to a model building in order to decrease the seismic vibrations. And it's, I think, important to add that Turkey is at one of the most active seismic zones, and there are many earthquakes still are resulting very significant damage. So we have focused on the seismic control with magnetorheological dampers, and we have focused on 5 to 8 story buildings, which is very common all around Turkey. And in the project, our goals was designing an optimum MR damper for a specific structure. That's what I said, 5 to 8 story buildings. And in order to realize that, we need a robust and precise CFD model, which can mimic or represent the behavior of the fluid and the MR damper. And another goal was generating a suitable and effective control algorithm, because MR dampers needed a control algorithm to make the semi-active control. And another goal was improving that control algorithms depending on the experiments. So the project was funded by TÜBİTAK, which is one of the biggest governmental institutions in Turkey, and they're supporting those kind of academic projects. And the project took 2 years, and we were 6 professors and 5 graduate students, including me. And there was one company, they also give us support for the control field and the shaking table tests. And the project is a multidisciplinary project, so we have different researchers from different areas, like from civil engineering, like from electrical engineering, and some professors are mostly experienced in the control engineering, etc. So I just put the earthquake map of Turkey, just to let you know how a dangerous seismic zone lies beneath the Turkey soil. This is from a recent publication showing the earthquake map of Turkey. And I wrapped up some important earthquakes in the history of Turkey. So the last one was the most disastrous one, which took place in 1999. Maybe some of them remember it. I was in the middle school, so remember it well. It was a very hard time for Turkey. And it's also important to underline that the MR damper, using the MR dampers in buildings, it's not used just to prevent collapsing, prevent a building from collapsing. And civil engineers have a different scale, as you can see below. I mean, apart from preventing the collapse, you can provide a life safety or immediate occupancy after an earthquake or after a natural disaster. So what we are aiming was increase the performance level of the building from, let's say, collapse prevention to a higher level like immediate occupancy, or making the building fully operational after the earthquake. So now, after the aim and scope, now let's focus on the MR dampers. And also I need to talk a little bit about the magnetorheological fluids, MR fluids, which is the smart material used in MR dampers, which provides that adjustable stiffness feature to the MR dampers. So basically the idea behind the MR fluid is just actually adding iron particles into a fluid. So this fluid can be any type of an oil, as long as it can carry these iron particles in the micro level. You can use any type of oil, and under the magnetic field, the particles inside this oil align along magnetic flux lines, and they create a chain-like structure, as you can see in the figure, and that structure creates a resistance to the flow. And the resistance to the flow, we all know that is measured by viscosity in the physical world. And this structure, the chain-like structure in the MR fluid, in some way also increases the resistance. So we see a viscosity change in macro scale. And so this feature opens the way for the adjustable viscosity or fluid or adjustable stiffness dampers. And another fact that the fluid is very quickly responding to the magnetic field. So you can make the control of the damper or the fluid in milliseconds, and you don't need a huge amount of power. With 1 or 2 ampere current, you can just provide the control. And here are the basic modes of the MR fluid. You can see there's a valve mode, shear mode, and squeeze mode. There are 3 modes are used in the literature. And the MR dampers are using the valve mode because the damper has a pressure-driven flow inside. So we are applying a magnetic field, as you can see with the blue arrow, to the annular orifice of the MR damper, and we create the variable stiffness in the MR dampers. There are also different modes like shear mode, which is making the control on a movable plate or moving boundaries. I mean, in the second mode, as you can see, the flow is generated by a moving boundary. And there is squeeze mode also. It is used in the literature. It's basically creating a resistance between the squeezed plates. So, of course, it's good to see what MR damper is. You're seeing an MR damper. I think it's from the Lord Corporation. The MR dampers actually same in principle with the conventional dampers, viscous dampers, but as an extra, it has a coil inside the piston head, and this coil generates the magnetic field to change the viscosity of the fluid in the annular orifice, and which, by doing so, it creates a variable damping feature. I mean, it provides the control of the fluid. So there are also different types of MR dampers, like monotube, twin tube, double-ended, you can find in the literature. There are also rotational MR dampers. They create a resistance for the rotational motion. And of course, it's important to see the applications. So I just wrapped up some applications. There are a lot of application areas, so I just put the important ones. So in civil engineering, the MR dampers are used in bridges, very common. There are a lot of implementations in bridges, and lots of papers are present in the literature. And also the building control is made by magnetorheological dampers. It is also a very recent active research area, but for buildings, the implementations are not as much as the implementations done to bridges. I mean, as far as I know, there are 2 or 3 buildings are present now. They are using, I mean, there is some kind of experimental buildings, we can say, but it is still an active research area. What we were doing was implementing an MR damper to a building. And they are used in sports cars, off-road vehicles. There are a lot of examples. And they are being used in biomedical devices. You can see the leg prosthesis in the picture. There is an MR damper is implemented. And of course, it's very important to remind you that, I mean, these implementations, there is a very complex control algorithms are working behind the picture, because you're making a semi-active control and you need to provide the best stiffness in every milliseconds regarding to the input signal. And this input signal, I mean, can be the road vibration, or can be the seismic vibration, or the acceleration of a building during a seismic event. I mean, and vice versa, etc. There are a lot of different studies are present actually. So it's a separate topic actually. I mean, apart from the MR damper, the control field is also a separate topic. And there are MR brakes are present. It's an active research area as well in automotive industry. MR clutches, you can see in the middle. MR dampers are being used to preventing recoil in howitzers, different types of guns. And you can see an MR brake in a virtual reality glove on the right side. And it's a very small application. As you can see, the MR brake used in the virtual reality glove is the size of a penny. So it's also important to underline that the MR dampers can be at any scale. I mean, you're seeing a MR brake in the scale of a penny. From that scale, you can see a very high, very giant, huge MR dampers used in the buildings. And just briefly to talk about the control, just in the civil engineering, basically we have three types of controls we are considering. So if there is no control, the excitation or the signal just affecting the structure, and structure responds to this excitation, just responding it without any control. It's the no control case. If there is an active control, in active control, you are creating a force, generating a force, and you apply it to the structure, which is decided. I mean, the magnitude of the control force is decided by calculating the data from the sensors. And in semi-active control, it uses the resistance instead of generating an external power. So the semi-active control is very resembling with the active control, but the important difference is in semi-active control, we are not generating a force. We are just using the resistance of a fluid in the MR damper case. So MR dampers are semi-active control devices. And they don't use a high amount of power, actually. They just use a minimal energy. And the energy is just used to change the viscosity of the fluid. It is, for MR dampers, it's around 1 to 2 amperes. So it's a very small energy, we can say. And just to see the literature about the MR dampers and MR fluid, the MR fluid is invented in 1950s. And from 50s to 70s, I mean, the idea was present, and there were different patents are applied for this idea. And from 60s to 90s, different researchers are made theoretical studies about the non-Newtonian flows. I mean, it's not actually about the magnetorological fluids, but this information is going to be used after 1990s to generate the MR fluid involved devices. So from 90s, the experimental studies had begun, and from 90s to 2010, there were a lot of experimental MR damper or MR fluid studies. I mean, MR fluid involved device, because there are a lot of different devices. The literature is from 90s to 2010. You can see a lot of analytical solutions approach presented for MR dampers or MR involved devices. And for last 2 decades, we are seeing the computers are involving in the studies. There are a lot of CFD analysis, finite element analysis, or simulation studies are present for the last 2 decades. So this is actually briefly what the literature is about the MR fluid and MR dampers. So let me get back to the flow chart, and let me focus on the characteristics of the MR fluid. So I'm gonna start from a standard Newtonian fluid. Then I'm gonna talk about what MR fluid is, how it behaves. So the standard Newtonian fluid, as we all know, the shear stress is proportional to the shear rate. So this is what we call a Newtonian fluid, and this ratio is called viscosity, basically. And we see in the nature most of the fluids having a constant relationship between these two variables, and we see in the nature Newtonian fluids a lot. But we also see different fluids, having different type of behaviors. For example, a fluid can show a thinning behavior like this one, and it might decrease its viscosity with increasing shear rate, like toothpaste or wall paints. Or it can thicken, it can increase its viscosity with increasing shear strain or shear rate, like cornstarch and different types of fluids we see. And there were also different type of fluids. They just stay solid after a certain shear stress and then starts to yield. And we call this type of fluids Bingham plastic fluids. And these behaviors, all these type of behaviors depends on the molecular structure of the fluid. So let's look at the MR damper, how it behaves. So at 0 ampere current or 0 Tesla magnetic field, the MR fluid just behaves like a shear thinning fluid. See, and if you increase the magnetic field, let's say for 0.1 Tesla, it starts to show a Bingham plastic behavior. It stays solid after a certain shear stress and then start to yield, as you can see. And if you increase the magnetic field, the yielding point is going upper. I mean, it increases. And by the way, it also shows after yielding, it shows a shear thinning behavior again. So there is a Bingham plastic behavior and shear thinning behavior are involved at the same time for an MR fluid. So here you can see at a high magnetic flux density, it's 0.8 Tesla for low MRF fluid. You can see the behavior and the yielding point. It is like becoming unstable at some point and then begins to yield and showing a non-Newtonian behavior. And this is the velocity profiles of a MR fluid across an annular gap. So what is important is it has a plug region in the middle of the flow profile, and the middle region, it is, because it is under the yield stress, it shows a plug behavior. I mean, the velocity profile stays constant in the middle, and in the upper and lower places, it shows a behavior of a flowing fluid. So for modeling this, fluid, we can use the Bingham model, which considers the fluid from after the yielding point. It considers the fluid as Newtonian fluid, and Hershey-Balkley model is actually used for non-Newtonian fluids. It's also used for blood and different kind of non-Newtonian fluids, and it models the fluids. It models the shear thinning and shear thickening behavior of the fluid as well, and it also models the Bingham plastic behavior. So it's a much more improved model, much more complex model. It has much more variables, and Bingham model is a much more simple model, which is used also in the literature for magnetorheological fluids. And let's focus on the numerical models. So we have used a 2D axisymmetric model for modeling the MR damper. I've just drawn the axisymmetric 2D model below the axis just to understand the whole model. Here, as you can see, the piston head, it moves back and forth or up and down. And the MR fluid is around this piston head, and there is an annular gap. Of course, this is axisymmetric. Just imagine that it's rotating around the piston head, and the coil is inside the piston head, and it creates the magnetic field. And this magnetic field creates active zones, which is shown in the red boxes. So we call this area as active region, and the MR effect is taking place in that active region. So this is what makes a MR damper different from the viscous damper. And we conducted the magnetic field simulations for 25-degree slice, axisymmetric domain, and created the CFD analysis for 2D axisymmetric domain. And here is the CFD model. As you can see, is a 2D model, and the motion has been modeled with moving boundaries in the left and right side, and a structured grid was used because we have used the moving boundaries, so it makes it easy to use a structural grid for our study. And the mesh convergence you can see in the upper right corner. So we have created our CFD model, and now the most important part of the study is the modeling this non-Newtonian fluid with a CFD solver. In the literature, there were two types of approaches are present, and both of them are modeling the MR fluid as a Bingham plastic fluid. And we have proposed 4 different approaches to be used in modeling the MR fluid. So there are 2 approaches in the literature, and we have proposed 4 extra approaches. So let me begin with the simplest approach, which is the Bingham uniform magnetic field, which is in the literature. In this approach, the fluid is modeled as non-Newtonian in the active region and Newtonian in the rest of the domain. So this is a 2-domain model, and in the non-Newtonian region, the magnetic flux is considered as constant. So here they do consider a constant magnetic flux. They modeled it as having a uniform magnetic field. So this approach is, of course, it's not a bad idea, since the active region generally having a uniform magnetic flux. So we have compared it with a previous study that we made, and we ended up that the results agrees with the previous experiment, but of course it can be better. And we also checked the other approach, which is the coupled magnetic field. So this is also present in the literature. And here you can see different magnetic flux regions coupled by cell. It's one-way coupling of the magnetic field to the flow. So the viscosity was calculated in every cell depending on the affecting magnetic flux. So the results also pretty good, having a good agreement with the experimental results, but still there is a difference with the experiments. So we have just, by the way, here is the viscosity contours of the coupled magnetic field approach. You can see the viscosity change. It's not a constant viscosity, and you can see the transition of the viscosity contours as well. Anyway, let me just talk about our approach. So we have started first with the MR fluid characterization, because we need to know more about the fluid and make a detailed analysis. So we have started our work by examining the fluid with our rheometer in our laboratory, and we used Anton Parr rheometer. So it's a rheometer which is designed specifically for magnetorological fluids, and we did have a chance to examine the fluid at different magnetic flux densities and also at different temperatures. And we did our study. We have reached pretty much the same values with the manufacturer sheet. By the way, the fluid was a commercial MR fluid, which is Lord MRF 132DG, I think. Yeah, this one. And after we did characterize the fluid, we've started to create our own approach. First, we have started with the Hershey-Bulkley formula because it seems that at first glance it seems that it's a better way to model the fluid with the Hershey-Bulkley because it shows a shear thinning behavior and also Bingham plastic behaviors. In this formula, there are three variables, which are tau O, which is the yield stress, K, which corresponds to the viscosity, and N is a index multiplied by gamma dots, and the N is representing the shear thinning or shear thickening behavior in the model. So there are three variables, and these three variables are affected or are the function of the magnetic field. So we just created a curve fitting polynomials and different type of equations just to fit these variables with the magnetic field. And the results came out not representing the behavior of the fluid. So we also tried different functions to represent this relationship, like exponential functions or trigonometric or different type of functions, but we didn't have a better result than this one. So we just focused on another approach, which is making an interpolation by using Hershey-Bulkley model with using the interpolated data. So we have created an interpolation matrix, and here one column representing the magnetic flux density and the three other columns representing the yield stress K and N numbers, the three coefficients that used in the Hershey-Bulkley model. And so for a given magnetic flux density in the domain, so we are making a cell-by-cell coupling. For any given magnetic flux density, we just go and match the values. Of course, we need to calculate the interval values. So we made it by using the interpolation formula. And here are the results. So the results are better than the curve fitting, but still it has a way to reach the experimental results. So we have generated another technique to calculate the viscosity, which is implementing the rheological data directly to the CFD solver. We call it direct viscosity interpolation. Because we know that viscosity is actually a function of magnetic field and the shear strain. So maybe it's better to totally get rid of the coefficients and of the Hershey-Bulkley curves, and we can do it by direct interpolation. And here you can see the matrix. This is the magnetic field shear strain matrix, and you can see the shear rate here, and you can see the magnetic flux density. So for a given shear rate in the domain, again, we are making this cell-by-cell coupling. So in every cell, you see a different shear rate and different magnetic flux density. So for a given value, you can just calculate the viscosity. So for, let's say, another shear rate or another magnetic field, you just can go and find the exact viscosity value. Of course, again, we need to use the interval values. So we created a 2D interpolation. You can see the formula for an interval point. So the algorithm works in a very simple manner. We have the parameter measurements converted to a file, text file, and imported to an interpolation matrix. And from the other side, we have the magnetic field analysis, and we just map the magnetic flux density in the domain. And the algorithm just calculates for every time step and for each cell the viscosity. So here are the results again. Results are very prospecting and matching with the experimental results, but maybe we need some improvements. So we just decided to create another approach, which is called the direct shear stress interpolation. And this time we use the shear stress instead of the viscosity. because viscosity, we know that the viscosity is the function of the shear stress or shear strain. So it adopts the same principle with the viscosity metrics, and here are the results. As you can see, are very matching with the experimental results. And this model is our best model actually. And after evaluating the results, you can see the results here. Here is the error values. You can see the shear stress interpolation having the smallest error with the experimental data. And you can see also the other approaches. Hershey-Balk interpolation is also having good results. And the coupled magnetic field, which is present in the literature, is also having good values. But of course, it's important to underline that the method that we have generated is actually can be used for different type of MR fluids and different type of applications, because it's only depends on the rheometer measurements. So if you have the rheometer measurements for any kind of fluid, which might be a non-Newtonian, which might not fit in any non-Newtonian model, you can just use that interpolation metrics and the algorithm, and you get the results. So here are the flow profiles, different approaches having different flow profiles inside the annular gap. So you can see that the profiles of the approaches that we have proposed having a more oval profile, like having more smaller plug region, and the other models like the analytical approaches or the other approaches having a bigger plug region, as you can see. And you can see the flow at 0 ampere at the right side. In the literature, the 0 ampere condition is considered as Newtonian, but with our approach, we also consider the non-Newtonian effect at 0 ampere, so the flow profiles are a little bit different, and here are the viscosity contours at under 1 ampere, different approach. And here are the viscosity contours under 0 ampere for the shear stress interpolation approach. As you can see, it's very different from a Newtonian approach. So there are some low velocity stationary viscous zones. You can see with that modeling, we get the physical results. So it is a kind of the picture of the physical structure actually, because it's not Newtonian. So there should be some high viscosity areas should emerge. It's something that we do expect. So here the viscosity contours at 0 ampere again for Hershey-Balk fluid. At 0 ampere, you also see a plug region, very small shear stress present because at 0 ampere as well. So I think we are getting out of time, so let me be quick. So this is our safety approach. So it's not easy to cover all the projects, so I'm going to go very briefly for the rest of the project. So depending on our safety model, we made an optimization study for the MR damper. We choose some parameters are changing, and we made our optimization study aiming to have the maximum dynamic ratio in the last row. You can see the dynamic ratio is actually the ratio between the viscous forces and the magnetically active damper force. So it's a kind of the definition of a range, what an MR damper can reach from the minimum to the maximum. So if the dynamic ratio getting bigger values, it means a good thing because you have a bigger range. So our goal was creating the maximum dynamic ratio with the prescribed force value. So the force value was 700 Newtons. So we have find the optimum geometry for the MR damper, and we have manufactured our MR damper. We made our performance tests under different velocities, temperatures, and currents. Here are the results. By the way, we compared our manufactured MR damper with its industrial counterpart as well, and we came across that we have better results than this commercial damper. Of course, it is optimized, but just to show you that we have better results in terms of the dynamic ratio. And here are the mesh conversions. We have used our CFD model with the produced MR damper as well, just to compare the results. Just briefly, I'm just showing you the results for different current values. Here are the flow profiles calculated for different conditions. And here is a comparison of the error values. And the error value of the CFD model is much better than the analytical approach. Just here and apply the viscosity controls again. At 0 ampere, you see a very small plug region, which is something physical because the MR damper has a yield stress even under 0 ampere. This is the contours at 1 ampere. And you can find further information in our publication as well. I just put it in the bottom. So find the publications if you're interested in this topic. So after creating the MR damper, we also worked on the dynamic models. These are the dynamic models, 6 different dynamic models we did, created the Simulink diagrams, and we tested these dynamic models. And we just concluded that the Bookman model, which is widely used in the literature, having the best values. And we also created an artificial neural network model because in the real-time application, we need to make an inverse model, and the models in the literature doesn't have the ability to make an inverse modeling. So to create an inverse model, you need something else different from the literature. So we have created the artificial neural network, and we have generated 3 different control algorithms. One of them is PID control, which is well known in the industry. One of them was sliding mode control, which is also very popular for seismic applications. And one of them was a new type of algorithm, which is energy-based control. And we created a software just to make the experiments and implementing the control algorithm. You can see that you can control the controller coefficients from the graphical user interface. We can train the neural network algorithm from our software and monitor the results of the tests. So let me go to the shaking table tests. Here is our model building, which is created with the reference of a 5-story building, which is used very common in Turkey. We have matched the frequencies, and here you can see 3 different building models. We do have 4 different building models from 5-story to 6, 7, and 8-story buildings. And on the right side, you can see our 6D OFF shaking table, which is manufactured by our industrial partner, Somnap. And you can see the specifications on the left side. And here are some test equipment which are used in the tests, like acceleration sensors, force sensors, data acquisition cards, and temperature sensors. And here is the test setup. The MR damper was installed on the 1st floor, and there are 2 earthquakes data were used. One of them is the Kocaeli earthquake, and the other one is the El Centro. So we have defined some evaluation criteria just to compare the success of the controllers. And here are the results. So briefly, I'm just showing you the results. You can see the maximum interstory drifts. Here are the general test results. So what we do conclude that our MR damper has a better performance of 23% from its industrial counterpart, Lord MR damper. So MR damper showing a very good performance. PID seems to be the most prospecting best algorithm. And regarding to the indexes, these indexes are for civil engineers. So J3 and J6 indexes. By the way, you can find further information about this study. I think I put our publication about that one as well. We will have a publication about this work. So regarding to J6 index is very important in buildings because it shows that if a building might collapse or not. It's the shear stresses in the building. So we get a reduction of 50% and 47% for different control algorithms. And I just put the videos of the tests just to make it more you to more understand the tests. And here is a test with no MR damper. So we did a test with no MR damper and with the controller, so you can see the difference between using an MR damper in the building and using anything. Also, of course, I mean, we did the comparison with the no control case with MR damper, and you can see another implementation with the controller and with the MR damper without control. So you can see the difference. Maybe this is the El Centro earthquake, by the way, which is very common in the literature. The sliding mode control is used here. There's another as well. This is 8-story building with the Kocaeli earthquake. By the way, the models are, I think, like 4 meters long. So maybe it's not so visible here to understand the size of the buildings. And let me just conclude the remarks. We have used 4 different approaches, extra approaches in for the MR fluid, and we get a very small error value with the experimental results. And these values are good enough to model an MR damper having an MR fluid. So the other approach is also having good values comparing with the experimental data. And with our proposed approach, we have a chance to see the non-Newtonian flow inside the MR damper and the flow characteristics of a non-Newtonian fluid flow. And these models can be used for any type of non-Newtonian fluid flow. And of course, it's better to use it for very complex non-Newtonian flow problems because it has the ability to model every single shear stress and magnetic field value, or for a different type of fluid. You can also add the temperature differences, temperature variation in your model. And one of our proposed approach, we use it for the optimization and manufacturing process of an MR damper, and which is validated once again and used in our shaking table tests. And for the project, the control algorithm PID showed the best results, which reduced the J3 index up to 50% and reduced the sliding mode, reduced the J3 index up to 47%. And it was a good value comparing with the experimental studies in the literature. And I think the artificial neural network is playing an important role behind this success. And we have concluded also that for the taller buildings, we might need more extra MR dampers, because in the taller buildings, where the performance is getting decreased. And if we conclude all the results, we see 50% decrease in J3 and 55% decrease in J6 indexes, which can change the performance level of a building from the immediate occupancy performance level to the life safety level. So it's very important for us. And as a future work, we have also started another project, which is a new type of tuned liquid column damper equipped with MR fluid. I mean, it's a damper, but it's very different. And we are going to use the MR fluid to mitigate the seismic vibrations. And it is also usable for offshore platforms. It's another project. So we are going to use our experience here in that project as well, because the controllers, the modeling of the MR fluid, and the CFD approaches, we can use all of our experience in the new project as well. And Also, our manufactured MR damper showed a better performance than its industrial counterpart, lowered RD8041 MR damper. So it is a success for us to have better results from the industrial MR damper. So thank you for your time, and just again thanking the TÜBİTAK, the Scientific and Technological Research Council of Turkey. They have provided us make this project possible under the project now here 115M363. We really appreciate TÜBİTAK, and here is the picture of our team. And if any questions, I'm ready to try to answer the questions. Thank you very much again for your time.
Thank you, Dr. Kemerli, for the nice presentation. And if there is any question, you can write it down in the chat or let me know so I can unmute you. We have a question from Bilal in the chat, and he said, thanks for the information-packed presentation, Dr. Kemerli. For the second interpolation model, how did you collect the data for viscosity? Also, would you think it's a good idea to account for any viscous heating from the MR fluid?
Okay, I showed the rheometer, that we do have a rheometer. It is a very good rheometer. It just collects the shear strain and shear rate and the viscosity for any strain rate. So we got the metrics from the rheometer actually. And accounting the temperature is also, this is an important question actually, because in MR dampers, the temperature also changes by time. So it is good to account the temperature. So actually in our project, we have started to account the temperature as well. And so we have also measurements for different temperatures, but we didn't involve it because in our tests, I mean, it takes like 30 seconds. So in 30 seconds, you don't experience a considerable temperature change. But of course, it has to be accounted for example, in the applications used in cars, for example, because the temperature really changed in a wide range.
Thank you. Any other questions? You can write it in the chat or let me know. Okay, Dr. Kemerli, I think I have a question about the different approaches you present to represent the rheological behavior of MR fluid. I think that the curve fitting one was away from all the other approaches.
Yeah.
Am I right? Or
yeah,
is there a specific reason for that? Like,
I think, I mean, the coefficients in the Hershey-Balkley model actually, it's very hard to create a fitting equation because I mean, there is no direct correlation between the K and N coefficients. So I mean, it's something very hard to match the equation. You cannot make it with a standard polynomial function. The yield stress is okay because it increases with increasing magnetic field, but the K and N coefficients are very hard to match it. Even we tried Fourier equations and trigonometric equations, but I mean, it's very hard. So that's why I think the results are very far away from the experiments.
okay, thank you. And we have a follow-up question from Bilal. For the 2D model, how did you make sure is not overfitting, meaning it performs well on different test data?
You mean, okay,
You can also take a look on the question from the chat.
Yeah, I'm trying to find it, yeah.
Yeah.
Okay, all right. So I think he's asking how we ensure that the mesh convergence, we did the mesh convergence for the model. So use the mesh convergence. And for the rheological data, we just repeated the tests to be ensure that we are using the correct correct value. So we're just repeating the tests. I think it's enough for us.
Okay, thank you. Any other questions?
So Muaz, is that overfitting that maybe is it only working for 2D? Is it possible that your tests only crafted for 2D and is not really representative of other cases? It's so too tailored for that specific case. Is that
so,
the case?
Yeah, I understand. Yeah, I mean the 2D, the MR damper. I mean it has a axisymmetric domain. So I mean very small differences that it has, but in the end it fits the 2D model because it's axisymmetric. So we also compared it with the 3D models. So we ended up with that there is no such a big difference with the results, and it's very easy for a 2D model to create a mesh convergence, because in the 2D model you are using very less mesh, so you can go make it very finer in the gap region. If we would have been used a 3D model, it's not possible to create the amount of mesh that we used in the 2D model.
Thank you.
Oh. Okay, we have a question from Hossein Abedi, and he said, thank you for the presentation. And he asking, are there any solid-based dampers competitive to the fluid-based dampers in the buildings?
Okay. Any solid-based dampers? Okay. Well, actually, we haven't compared it with the solid-based dampers. But if you consider the 0 ampere condition, it's actually pretty much the same thing with a viscous damper, because we don't apply a magnetic field. Of course, the fluid is a little bit different, but it shows the behavior of a viscous damper at 0 ampere. So when you increase the magnetic field, you just creating infinite amount of dampers. Actually, we can just imagine it in that way. So we don't have any comparison actually, but can go with think in that way.
Bilal has another follow-up question. He said you showed a neural network at the end. Did you get a good deep learning model to predict this viscosity, the viscosity?
Well, I never think about using the neural network in viscosity. Actually, we have used it just to model the input current. I mean, the response of the MR damper regarding to the input current or the magnetic field. So it might be a good idea, but yeah, it's worth to try. Yeah.
Thank you. I think that's it for the questions. Dr. Amili, you want to conclude?
Thank you so much, Muaz, for your very informative talk. To just a quick one, to give us a perspective, how costly these systems are and how complicated to set up and to maintain, and how widely they are used in Turkey at the moment.
Well, it's a good question, because it costs very much. I mean, that's why there is no much implementations that we see, because there are just 2 or 3 implementations in the world, and those implementations are pretty much for the experimental purposes. I mean, it's not something industrial. So what we did is, from the academic perspective, just to model the MR dampers. But if we come to the cost of the MR damper, it's too much for now. How it can be feasible for using a wide implementations? So it needs to be compatible with for serial production, mass production, because in our project we have also manufactured our own fluid. I mean, from Istanbul we did have another researcher, and she created the MR fluid by herself. She's in the material engineering. So it's not a very expensive thing. I mean, you just add iron particles in an MR fluid. So if you just create your facilities for mass production, it might be feasible to be used in wide range. But of course, it's not something that is easy.
Thank you. Any other questions from the audience?
No.
All right. Thank you, Muaz. Thank you so much for your time, and thank you, Karim, for organizing. See you guys in 2 weeks.
Thank you. Have a good day.
Have a good day.